Hi, my name is Anne-Marie Fortuna, and I'm here to discuss the use of indicators of soil and water quality to monitor shifts in natural resources and climate. I work at the USDA ARS Southern Plains Grazing Lands Research Laboratory in El Reno, Oklahoma. Our mission is to quantify the interactive effects of land use, agricultural management, climate, and the water cycle on agricultural and hydrological systems, the development and use of planning tools to evaluate and manage environmental risks under variable climatic conditions. Our unit is a part of the ARS Conservation Effects Assessment Project, or CEAP. Our team goal is to develop and implement a web-based data system using historic and current climate, water, soil, and land management data sets from long-term ARS research watersheds to assess conservation practices and conduct hydrological analyses. Our research is also an integral part of the Long-Term Agro-Ecosystem Research network. Our global objectives are to combine geospatial data and landform element classification schemes to derive landform complexes used to codify the collection of soil and water data at variable scales. Indicators are then used to determine the optimal time required to improve soil and water quality after adoption of conservation practices and systems that incorporate stacked conservation managements. Managements include cattle grazing at low stocking rates, cover crops, minimal tillage, and precision fertilizer applications. I'm a soil scientist, and I hope by the end of this talk you understand the value that soils has with respect to hydrological modeling. Specifically, biogeochemical cycling in soil is defined as the transformation of elements between non-living and living matter, and it's a conduit across land, air, and water interfaces. Soil functions include sustaining biological diversity, activity, and productivity. So whether a particular field can support different crops and managements is partly dependent upon soils. Soils also regulate water and solute flow, filter, buffer, and degrade organic and inorganic materials, store and cycle nutrients, including carbon, and provide physical stability and support. So land management and water quality, defined as runoff, suspended sediments, nitrogen, and phosphorus, are inherently linked to soil quality, defined as the productivity of agricultural systems and their impact on the environment. But linkages between water and soil quality are often limited due to the number of samples that are required to capture both the spatial variability of a given measurement and that of terrain attributes. As a result, new approaches are needed to reduce sample numbers and the time required to prepare and analyze data. Some of these technologies are not necessarily new. In fact, remote sensing and radiometry have been around since World War II, but what is different is our computational capacity. So until about 1980, in the advent of computers and ecological scale data was limited by our ability to not just collect samples, but to process data. And this was even true at the proximal scale, such as the soil pedon. Now, because of big data, we can look at genomes, and also the advent of nanotechnology enables us to collect in real time, in situ measurements of gases using microsensors. Even radiometry measurements in situ to predict soil and water quality require computational power that we have only had recently. And when we scale up to the distal, such as the Fort Cobb watershed, and look at remote and proximal sensing, the same is true. At the global level, digital imaging analysis requires even more computational skills. So hopefully, once we've established our baseline metadata sets, we can use some of these technologies to predict part of our data, which would hopefully enable us to analyze information in real time to aid growers in land management decisions. So not just to forecast, but to make decisions at the moment in the field. At the GRL, we conduct research on watersheds at 3 spatial scales. There's the field scale, represented by the water resources and erosion watershed on the left. These watersheds are 1.6 hectares each. At the field scale, or production scale, rather, we have the green farm. It's the Southern Plains LTAR green farm. These parcels represent a size that's more comparable to a grower's fields, ranging from 10 to 20 hectares. And then finally, Fort Cobb, it encompasses kilometers of area, but a given management is likely to be more on the order of 40 to 100 hectares, so another order of magnitude larger. Each of these watersheds represents topographic, physiographic, vegetative, and agricultural conditions typical of the Southern Great Plains. Specifically, management systems in all research watersheds include conventional cropping systems, such as winter wheat, grown under conservation and conventional managements, both integrated with integrated livestock components. The other portion, about 50%, is managed as grasslands, either native or managed grasslands that receive nitrogen, fertilizer, and fire management periodically. But before we can talk about conservation practices and their effect on soil and water quality, we have to delineate and limit spatial variability related to terrain attributes. So uniform zones of management are delineated using Class 1 soil survey measurements, grid sampling, and then the information that we obtain from soil samples and water sampling on the grid is used to create the uniform zones. This enables us to assign the remaining variability in soil and water quality to land management, a specific conservation practice, or stacked practices. Now we're going to talk about an actual example. I only have time to discuss one watershed, so I chose to focus on Fort Cobb. It's the largest, and it has the most historic data to work with as well. So at all 3 sites, our work addresses the design, technical measurements, and statistical methodologies used to link soil point measurements across variable land use and conservation. In this example, the diagram in color represents different soil series. So each soil series is a different texture. And then the circles that are in black represent the variable land use and conservation. At each of these points, we took, or an individual took soil quality measures that were used to create an index. That data can then be coupled, it hasn't yet, with bi-weekly water quality measurements taken at adjacent locations, similar, just adjacent to the soil samples. That's the black dots in the white map. And then in addition, climatic data can be overlaid and correlated with this information. This data was collected using meso and micronet sites. So in addition to air temperature, we also have soil temperature, rainfall, relative humidity, solar radiation, and volumetric water content. So with these metadata sets, we can then begin to predict soil and water quality at variable scales. So ideally, once we have a baseline, measurements that vary with agronomic management that are collected from the spatial zones that are uniform, these samples can be used to monitor, parameterize, validate, and predict the effects of alternative land management using technologies such as radiometry. So in the example of the radiometer, it can be used in situ or in the laboratory, but the benefit is that once we have the baseline, we can use a smaller subpopulation in the future to determine shifts. So if we started with 100 samples, then, and we had a validation that was sufficient, in the next sampling, we would take 10 random samples and actually process those. And the other 90 locations we could pick and either measure in situ with a radiometer or use the radiometer in place of the laboratory analysis. So this is a big step forward to being able to scale up. And if we use remote and proximal sensing, it's a more of an in situ measurement. Likely we would have to use the radiometer in situ to verify that we could actually use the proximal sensing at the Fort Cobb site. An additional important tool is multivariate analysis. It's another means of separating terrain attributes from conservation management effects, and it represents variations in soil and water quality that are related to these two attributes. Let's take an example in which we use multivariate to assess soil quality. In the first example, this data is taken from Fort Cobb in 2006, and it's from 4 different treatments: the native and managed grasslands compared to the 2 agronomic managements in winter wheat, one under conservation and the other conventional tillage management. So what you're looking at is an ordination analyses. So each of those points represents all the soil quality measurements and their position in 3 XYZ, so 3 coordinates. So any point that is close to another point or on top is not different or more similar. And the points that are farther apart are more different. So the points that were taken from the grassland treatments clustered over top of each other and in the same ordination space, suggesting that they varied very little. Additionally, the conservation treatments clustered adjacent to the grasslands, which suggests the soil quality parameters have not varied much since the treatments have been put into production under conservation management. In contrast, the conventional cropping system is farthest away and suggests that the soil quality parameters are beginning to vary, and in this instance, carbon values are decreasing. So next, I'm shifting to the field scale, the WRE. I took these samples when I first arrived in 2018. So this multivariate analysis is slightly different, but it's the same concept. I took the suite of soil quality parameters, most of which overlapped with the ones we just saw. There were some variations. And I looked at how each of those points clustered in 3 dimensions and ended up with a similar relationship. So the conservation management in winter wheat overlapped with the native grassland baseline, and then the conservation management differed. It was farthest away from the conventional management. So this is the winter wheat that was tilled. So you can see that these are different scales and different soil textures taken at different time points, but we got similar outcomes and a similar interpretation. So again, multivariate is a very powerful technique. So in conclusion, I think our research has inspired new approaches and collaborations. It will continue to leverage soil health to strengthen our understanding of the soil and water nexus. And how we're accomplishing this is by using some of the historic and current data at all watershed scales in the LTAR and CEAP modeling projects to link soil and water quality to stacked conservation management practices. In addition, this summer we included began to use Fort Cobb watershed information in the dynamic soil survey that links raster soil maps that are similar to traditional soil mapping techniques with dynamic soil properties such as soil health, hydrological measurements, and ecological site descriptions. So this is an exciting step forward and a good additional relationship that we have with NRCS. And then finally, I think I'm most excited about using the technologies such as the radiometry and the proximal and remote sensing with the ground truthing data to aid growers in making informed, fact-based decisions in real time. So with that, I'd like to thank all of you and open up the floor to questions.